Okay, so that's a little bit about the technology. What does the data look like? It starts with a waveform or a laser pulse. Some systems capture and record that waveform, and some systems don't. Some systems go straight to measuring or recording a point. But in both cases, we have some record of signal strength. So for every one of the points that you can see in this point cloud, usually there will be a measure of signal strength, or what we commonly refer to as intensity. It's not, strictly speaking, intensity from a physics definition point of the world. It's really just the amplitude of signal strength. So we would refer to this image is essentially made up of these peaks in the waveform, the amplitudes. But the kind of products that we're more familiar with usually are the surfaces that we can derive from these point clouds. So in this case we've got a digital elevation model, or in this case we've got a 3D model of an urban landscape. And of course we can extract biometrics from forested point clouds. Now I just wanted to illustrate here that different scan configurations will give you different types of point cloud attributes. So in this profile through a point cloud, what we're looking at is a terrestrial laser scan, where the terrestrial scanner is located somewhere around about here. So we see a lot of information in the understory, and then as we get into the overstory, we start to see some attenuation, although we might not really know there's much attenuation there until we integrate the airborne data with that. So this is a cross-section of exactly the same area, but now looking at it with airborne, or from the airborne perspective. If we put the two together, you can see that the terrestrial has missed the tops of the canopies due to occlusion from below, whereas the airborne doesn't give us quite as much information down below. And of course we would expect that. That's just simple geometry. That's just a function of the perspective that the different scanners has. But it is worth bearing in mind if we're integrating these data sets for any kind of information extraction. Now, one of the beauties with contemporary airborne LiDAR technology is that we have multiple return capability. What that means is for every single emitted pulse, we can capture multiple reflections. So an example I like to use when I'm standing at a podium like this is if we had a pulse of light coming down and it hit the edge of this table, some of the energy would be reflected from the top surface, some of the energy would continue towards the ground, and some would be reflected from that ground level. And so it's the same in a forested environment. We can simultaneously capture the tops of the canopy, major reflecting elements within that canopy environment, and also the ground at the same time. If enough energy makes it all the way to the ground and makes it out of the canopy on the way back, then we'll capture all of that information at the same time. Some systems will record the entire waveform, and so you need to post-process that waveform to extract those reflecting surfaces, whereas other systems will do that on the fly and will compute the actual reflection positions in real time. And incidentally, it's probably worth mentioning that the emission rates of systems at the moment is probably up to about 1 million per second. I'm not sure because it changes quite frequently. As of 2004, which is when we acquired our airborne LiDAR system, the state of the art was 100,000 pulse emissions per second. And for each one of those emitted pulses, you could theoretically capture up to 4 returns. So what that meant was, in theory, you could capture 400,000 measurements of the three-dimensional nature of the landscape every second. Of course, that was 2004. We've moved on 10 years since then, so basically we're talking millions of measurements per second now of the three dimension of the landscape. So it's quite impressive in terms of the detail that can be captured in the landscape. Just to illustrate some of the differences in point cloud attributes here, again we've got that terrestrial hemispherical scan. By hemispherical, what I mean is the scanner is mounted within a plot and it scans all the way around it, so it captures the full hemisphere. Here we have a high resolution airborne laser scan and a low resolution airborne laser scan with different systems, and all of these data sets are coincident. So, you know, the obvious thing that jumps out is the difference in density. But let's take this, the higher resolution scan, and then divide it into primary returns and secondary returns. So just going back to this illustration, I would consider a first return to be a primary return and a last return to be a secondary return. Also, if you hit, say, a parking lot floor and there's no interference with that pulse, then that would be a single return, which would also be a primary return. So we can see there's a difference here in the primary and secondary return attributes. There is more density in the primary returns, and there's a tendency for more primary return information at the upper level of the canopy and also at the ground level, whereas secondary returns, the distribution is less bimodal. Anyway, let's not get hung up on the details on that. Just suffice it to say there is different information content in those primary and secondary returns, and so that's worth bearing in mind if you want to do some modeling on the point cloud. Of course, what has really driven the development of the technology is the desire to map ground surface or generate digital elevation models. And so because this is an active sensor, the pulse sizes range from about this big to slightly beyond where my arms can stretch, but that's the typical range of size for an airborne LiDAR footprint on the ground. But given that kind of dimensionality, it means we can penetrate through canopy environments, and given the multiple return capability, we can simultaneously capture the upper elements and the ground elements. But of course, if there's more foliage, then less of the energy will make it to the ground. So very, very, very dense canopies can actually totally occlude the laser pulse and lead to no ground returns. But that's actually quite rare. We do tend to get some sampling of the ground surface, and so airborne LiDAR has proven itself very good at capturing ground surface data, even in forested environments. And so what that allows us to do is two things. First, we can take the all hits, all of the data. We can generate digital surface models of the upper elements of those point clouds and generate detailed maps like this. So here we can see the floodplain, we can see buildings within an urban environment, we can see forest stands. So all of this information about the surface of the landscape that we can see from the air just jumps out at us in high detail. But because this is an active system, because we can penetrate through that canopy environment, we can see the ground, we can apply morphological filters or statistical filters to the data to remove those upper elements and leave behind just the lower elements. And so that allows us to generate these accurate and detailed digital elevation models. And so really this is what's driven the airborne LiDAR industry. It's this capability to really see the terrain and use it in a wide range of applications. I guess incidentally it is worth noting that water resources, or rather flood risk assessment, is one of the industries that really pushed the industry along in the early days, particularly in the US and in Europe, due to a desire to assess flood risk much more accurately, and the very rapid realization that if you've got data like this, you can do that. So I previously mentioned that the point cloud had multiple returns. So here, this is what we can see here. Reds represent single returns, so there's only one contact for that emitted pulse. Blue, which you can see throughout, represents the first return, the first reflection. But for any blue return, there also had to be a second return, or a third, or a fourth. So yellow represents last return. So that means there's no more return or no more reflection after that one. So, as you would expect, most of the yellow returns or last returns cluster around ground level. However, it is important to bear in mind that just because a return is the last return or the last reflection that a pulse observed, it does not necessarily mean it's ground. And so you can see that here. We see a number of areas of yellow or last returns kind of embedded within that foliage mass there. And clearly that's not the ground. And greens are just intermediate secondary returns, so they would be second or third returns, somewhere in between the first and the last. So of course you never see an intermediate return at the canopy surface or at the ground. So what that tells you is that the echo code, the return code, sorry, echo and return is used synonymously in this community. So that return class actually has some important information that you can use in other post-processing. Here we see the intensity or the signal amplitude. Typically we'll see increased intensities at the outer envelope of the canopy, and higher intensities at ground level, just because, well, at ground level there's a much larger surface area for the pulse to interact with, whereas at the upper edge of the canopy, that's the very first thing that the pulse interacts with. So there is a systematic tendency for elevated levels of intensity in those two regions, and then you tend to see lower intensities within the canopy. Here we can see this is a point cloud with the it's color coded by elevation, but then the signal intensity is the grey scaling that you see there. So the blues just signify that's the lower elevations, and the browns and greens represent higher elevations, but the shading that you can see is the signal intensity. So these white lines, for example, clearly that's not a three-dimensional attribute in the data. Those are actually the white lines in the street, and it's the intensity that brings those out. And these patterns on the roof, I don't know if that's differences in moisture on the roof or patterns in the tar on the roofing materials, but again, that's the signal intensity that brings that information out. Here we look at a coastal wetland environment. So the signal intensity here is very useful in illustrated zones of moisture and channels. Water, when off nadir, gives a very weak return, very weak backscatter, or no backscatter at all. So it's either a data void or it's very low intensity. So water stands out very, very well at off nadir angles. At nadir angles, you get specular reflection, so it just saturates, it gets very, very bright. Another example, similar kind of illustration. And this is just looking at the Old Man Valley, a few hundred meters away from here. So we can see actually the effect that I just illustrated. Here we've got the nadir part of the flight line going over the river floodplain. See, we don't see any variation in the intensity over here because these are typical urban, rural, vegetated landscapes, so somewhat Lambertian in character. We don't see any clustering of the intensity values there. However, when we go over the river floodplain here, which is very wet, we see the intensities are very bright at nadir. And then as soon as we go off nadir, then they go very dark again. So just to illustrate, the flight line would have been across the image in that direction. A little bit more on intensity. This is a glaciarized environment. So the darker areas are ice. It might be dry, but I can tell you that in the darker parts of this ice, it's probably wet, it's actively melting. So again, we've got signal loss because of the presence of water on that ice. The bright areas are dry, snow, and then the intermediate areas are fern or multi-year snow that has got a higher moisture content. And so, you know, the intensity alone is not good enough to accurately classify those different strata. But visually, you can see the distinctions and the boundaries between them. So you can use the intensity to aid in classifications of this nature. Although we can't do straightforward classification thresholds, but that information can help. And just looking at the influence of moisture in an agricultural field environment. Actually, unfortunately, I don't think this is a particularly great slide, but maybe if you just look at this area. This is a period when the field was dry, and you can see the intensities are fairly high. And if we look at the same field over here, this is when it was wet, and there is some kind of patterning in there associated with the moisture patterns in there. Now, I'm not suggesting that the intensity is a really good index of soil moisture, and we did a study on this, and we kind of suggested, well, no, we can't map soil moisture with intensity, but soil moisture does impact intensity, so it's something to bear in mind. And I've got an image sequence here that kind of illustrates that. So here's another field in April. You can see we've got a kind of a zero order stream here. There's no running water there, it's just a depression in the landscape. But then by May, everything's dried up, there's nothing there. But maybe here's the interesting thing, by August, it's even more dry, but it starts to get darker again. And I wanted to illustrate that because what's actually happening here is this field is starting to grow. Whatever the crop is, I don't recall the specific details, actually I think it was just hay. But the point is, if we go back to May, all the vegetation's flat. So it's quite highly reflective. But then in August, the vegetation started to grow, which means when the laser pulse interacts with it, it's scattered in more directions. It doesn't reflect back quite so evenly, and the pulse reflection returns over a broader length of time, length of space, and so that leads to a kind of a flattening of the waveform, which reduces the intensity or the signal amplitude. So what that means is the kind of heterogeneity in the intensity that we see there is an index of the vegetation properties on that land surface. I guess just to illustrate some of the cool stuff you can do with point clouds now, if you've got a LiDAR integrated with some kind of imaging system, then you can take the imaging data and color code your XYZ easting northing elevation point. So you can add an RGB or some other kind of color channel information to it. So this is actually a 3D point cloud. This is not an image per se, it's a point cloud where every point has a position and some color information associated with it. And this is Niagara Falls, and the image is courtesy of Optech.